My name is Devadipta Dey. I am a researcher in Microsoft Research AI in the Adaptive Systems and Interaction group. So today I'm co-organizing this session on AI for AI systems. Just a little bit of background. My background is actually neither systems, but it's actually machine learning and robotics. So this is a fun anecdote I always like to say. From my robotics days at Carnegie Mellon, I was once part of a team that was building a big self-driving vehicle of some, not exactly a road vehicle, but an off-road vehicle. And there was this large number of sub-teams. And there was this one sub-team which was, let's call them the rock detection team. And the rock detection team decided that our aim is to build the world's best rock detector so that self-driving cars won't drive over them. And we can avoid them and do path planning and everything pretty reliably and robustly. So they very quickly built up the first nominal version. And this rock detector was good. It was like, on all our test data sets, proprietary test data sets, they were like 70% accurate. So to not hold up the rest of all the modules that were being developed by all the other teams, they decided that, okay, we'll push this out, let the team work with that, and then we will come back and we will try to improve it on the side while the rest of the teams are using this in the pipeline. So 6 months later, they suddenly come back and they say, hey, we have a 98% accuracy rock detector, and it works great. And we have the same function signatures and API interfaces. So just drag and drop this back into the code base, do a pull request, you're good, right? And so everybody was very happy, and they went and they pulled from upstream, and then the system just broke down. And this is a theme we kept seeing over and over again, that as each individual module was improving locally, the entire system would degrade. And when we realized that, the systems that were downstream from it, or sometimes even upstream from it, were learning to compensate for different distribution of outputs. And when I joined MSR, there was and it was in Eric's group, and Eric and me had always had these long discussions about how we build systems nominally. And the systems, we just build them, we try to do our best to optimize them, to make them as fast as possible. But our systems don't reflect, they don't adapt really, and to limited computation, the concepts of bounded rationality, and the fact that we will always have partial information and finite compute, especially on edge, robotics, the new classes of doing machine learning on serving or training as fast as possible, interactive systems. So I feel like this session is very timely, because just as systems has now enabled a new revolution or the new boom in AI, so as to speak, and large big data is now really big data, and new hardware, new chips, new systems are being enabled. There's also this question of how do you use AI to build better AI systems? So it's kind of a nice self-referential loop, and hopefully we will take off. We have an exciting lineup of speakers to talk about all sorts of themes related to this. First of all, we'll start with Eric. Just as a brief introduction, Eric is the director of MSR AI, and he also heads all of Microsoft Research, and we are very pleased to have him start off. And then he will be followed by Virginia Smith, who is just starting as faculty at CMU, talking to us about machine learning in the edge and how to do federated learning better. And then we will have Behnaz from the systems groups at Microsoft Research, and she will tell us about how machine learning is being used and what are the problems in networking, databases, VMs, in the cloud, and in really true big systems, how to do troubleshooting better. But without much further ado, I'll hand over the mic to Eric.
Thanks. I think I have a mic that I'm actually wearing. So for many years, since my dissertation work, I've been fascinated and intrigued at models of reflection in AI systems. What I mean broadly by that are representations and inference strategies that actually look at existing uncontrolled or unmoderated AI systems, and that come to control them and optimize them both for different kinds of distributional settings, shifts, for example, in streams of instances, varying amounts of time available for computation to generalize the ability of an agent to do well in the open world, and thinking more deeply about potential architectures of intelligence that might involve one or more layers of reflection, including reasoning about reasoning or meta-reasoning. And I thought I would just mention 4 topic areas today that I think are interesting directions in the realm of reflection. Learning to control inferential processes, given a base process. The idea of using portfolios of components to build more robust systems. Meta-reasoning for ideal allocation of resources, for this idea of being more flexible to distribution of problem instances, as well as to a utility function, for example, over time criticality. And then talking a little bit about policies and predictions for speculative execution, executing with available resources now about the future. These are all obviously interrelated topics. So first on this idea of leveraging, learning to control inferential processes. So for me, the canonical problem in this realm was some work we did that was published at UAI, which was looking at a theorem prover, looking at NP-hard problems to do satisfiability, constraint satisfaction problems, and other related problems. And we had access to a theorem prover, several theorem provers actually. And the basic idea was we would be given hard problems, and then we'd run the systems, and the community noticed that a solution could be found very quickly or take a very, very long time. And I mean, like many, many varies. In fact, there's actually a halting problem as well with some of these with these challenges. And it was unclear we actually knew how to discriminate problems that would go fast versus slow. On top of that, we had access to this idea of randomization of a seed that would start a new version of an analysis of a problem. And we can, so when you start a theorem proving problem, you can let the system run and run and run. And at some point in time, you can say, you know what? I'm going to stop this and restart it with a new randomized set of settings and try again to try to find a solution. And it was noticed heuristically by Carla Gomes, actually, and Bart Selman, that you could actually, by taking a whole workload of instances and running them through a theorem prover and moving a restart time for the distribution, just like keep on moving it. And when you restart, you throw away all your investment. So you're hoping to find a short run that will solve your problem at the cost of many runs. And they were heuristically setting these systems. We said, well, I wonder if we could do better than that. So the basic idea was, we said, what might we do from the point of view of a machine learning problem to basically look at this in a Bayesian way? And we first said, let's look at the instances and try to characterize the actual instance by featurizing it. Let's actually, the instance itself, let's featurize the environment where the generator that's generating the instances. And then when you run the system, let's take a whole pattern of evidence, like actually we featurized the actual search tree. What's happening in the initial part of the run here, and how long has it been running became a feature as well without finding an answer. So you can have that could be part of your feature space. And magically, I remember this, I actually was running WinMine on an airplane, cut off from the world in those days, with this big data set traveling across the country. And we discovered there was actual rich signal in the actual evidence being spewed from the theorem prover. You can read about all the distinctions in the UAI paper to build a model that would predict for any run, would this be a short or a long run in advance of the run completing. And this led to a body of literature, several papers, where we showed you can actually use machine learning to take a very hard, working on an NP-hard problem and cut through the hardness space with Bayesian inference about when to restart and randomize, and showed how you could extend the power of one of the hardest AI problems we know. They're improving. With one example. Another example of reflection I think we need to think more about as a community is how do we take portfolios of solutions and bring them together in a coherent way to make more robust reasoners. And the canonical version of this for me is a face tracking problem that I worked on many years back, but it actually also resonates with today's work and going on even in this room. I see Bessa doing work in this space as well to understand context-based performance and instance-based performance of a machine learning problem, for example. In this case, we're looking at face tracking here, and the idea is to take successes and failures and build a model of confidence, which is so important in AI systems in the open world. In this case, we actually had this idea of, we had an algorithm of a certain type that would actually provide us, we were interested in the inferred state where the face was. There was the idea of ground truth, which influences that. And then we had this idea of some interesting variable here, a very important one called inference reliability, real-time reliability of inference. And we couldn't see this directly in our algorithms, but we could actually view what we called reliability indicators. And each algorithm we tried had different reliability indicators, and we built a different model for. Now, it turns out that we could use different kinds of approaches in those days. Color-based model, motion decay model, we called one. This idea of background subtraction. But the fun thing was we built a model for each, we learned the model for each of these things, wove it together, and boom, we had a much more reliable face tracker. What I found most interesting in this approach with the portfolio is these are independently developed algorithms. Of course, you can find dependencies of various kinds and how they work. But I was excited, and you can read about this in the paper, in that we were now handling unmodeled situations in the open world. So, for example, we never really trained the system on this problem of facing away from the camera, or a jolted camera, or a peripheral distraction, another person walking through the scene, or turning lights on and off. But you see, since these are very different algorithms, and this led to the initial intuition as to how we built the system to begin with, this approach. You see, in different settings, one or more is fuzzing out. But the reliability indicators are quite robust to capture and wave and say, I'm not doing well right now. Weight things to the inferences from the other system. And in the end, you ended up with robust output. Just a generic approach to thinking through the possibility we can do this with other algorithms in the future, especially independent cuts on a problem that are each managed, and for each we have a reliability signal. Now, on meta-reasoning for ideal resource allocation, this is a really a powerful direction for systems we're building these days, and I'll get into that in a minute, but I want to go back in time for a bit to my own dissertation work, where I was very excited about this idea of thinking through what I used to call object-level value, and then comprehensive value of any inference in the world when you subtract the cost of reasoning, the cost of delay. So let's say we have an algorithm that's producing, given some utility function, with computation time, this upper curve here, in this case showing a monotonic increasing with decreasing marginal returns, and the idea of some notion of the cost of delay, in this case linear. And if you just consider a very simple model of we subtract the cost from the value, it's all on the same scale, you end up with this idea of a net value of action with time, looking like this middle curve here. And you see there's an ideal stopping time and an optimal amount of value you could squeeze out of this algorithm in this current setting. And if you made the cost of time a little bit more urgent, more critical here, more costly, in this linear sense, of course it could be any kind of function, you end up pulling back the amount of time you should be dwelling and how the ideal value you get out of the system. Now, of course, for the distribution here, this is all uncertain, and that's where it gets interesting. The expected value of computation, for example. So one way to exercise this system was to build approximation algorithms for probabilistic inference, another NP hard problem, it turns out, graphical models. And with time here, one algorithm called bounded conditioning would solve a decomposed version of a Bayes net problem with cycles. And you can see over time, the upper and lower bounds are converging. In this case, it was actually an urgent medical inference where a patient is standing by with gasping for breath. And our system actually is predicting at any moment, if I invest this much more computation in the system, here's what I can expect the bounds to do per being converged. It turns out that you don't know where the bounds, this particular algorithm, you don't know where the bounds are going to be, you just know how tight they're going to be. So you're uncertain, and you can integrate over that and compute the expected value of computation for 10 more seconds or 5 more seconds of computation, and therefore have a stopping rule when the expected value of computation goes to 0. Now, these methods, it turns out, stimulated work in part. If they cite the old work in the AI community, in psychology now, and people are finding these kinds of curves, very similar notions right now, in humans and other primate studies that are being done in terms of responsiveness, cost of the urgency of a setting, and the ability to do well with incrementally with more time. But let me talk about an application now of this, the modern variant that it's exciting me, and this is work led by Day and Dan Bohush. The idea is thinking through a challenge we have and an opportunity to build what we call integrative AI systems that have many components. In particular, these kinds of systems that can do learning and inference about a social setting, for example. How many people are in front of me? Are they talking to me? Where's their attention? What's the next dialogue step? What are people saying? So it's natural language processing, speech recognition, acoustical analysis of where sounds are coming from in a scene, like the assistant by my door, which after how many years did we take down? 7 years it ran straight, helping people, mostly straight. I would complain when it was down, like, where's the assistant? And we got it back up again. But anyway, here's an example of one of these systems, but you get a sense for the kinds of things that you need to do in these systems. Face tracking, listening. This gives you a sense for this in this quiet video, because there's a soundtrack here of how an agent might work with people. And the same thing in this case with physical incarnations that are physically embodied in robotic settings. A lot goes on that requires multiple components to work with one another. And so there's a platform we're building, and there'll be a workshop on this platform in a week or so. Okay, week or so is a good enough approximation to get a yeah from. Looking at Dan, who leads the effort, the SCI effort, which stands for Platform for Situated Intelligence. But the idea is to build a platform and programming model and execute it and runtime that can make it easier for developers to build a system that can take in multiple sources of input. So it's multimodal, with vision, speech, sound, acoustics, and so on. And then have many pipelines that do a sense, think, act kind of loop, where timing is very important, including calling for cloud components. Multimodal, timing, uncertainty, and now looking at meta-reasoning. And so, quick example here that they put together, leading this effort on the meta-reasoning challenge. We have these general graphs of components that call upon one another. For example, a system that might compute from LiDAR, camera, and radar, steering angle, brake force, and accelerator in a semi-autonomous vehicle. Might be some loss function of latency and accuracy. And we might sort of figure out, well, how do we want to prioritize and look at the trades between how well each component is doing, how much precision we need, versus its latencies that might affect the whole system and for the throughput of the system that's captured by a loss function in the output here. And one example that's what we're exploring is this idea of a face detector and landmark recognition component, where an image stream comes in. There are maybe 4 different algorithms, let's say, and we want to have some notion of computing latency and quality, but right now we're going to focus on latency. And we find this context dependent in terms of, in this case, the number of faces in a scene. And we're looking at 2 different settings here. And what they did is and Dan worked very hard to characterize how fast the system can respond with a square, a bounding box around the face, given different algorithms and given different numbers of faces in a scene, 0 to 4 in this case, in terms of milliseconds. If we actually give this system, come up with a utility function here, in this case around 450 milliseconds, we basically design a system that penalizes the overall function of the system based on time after this ideal target point. And then we want to sort of reason about, build a system that can actually learn this automatically from streams. And so the approach right now that's being explored is having a meta-reasoning module that's actually based on the theory around contextual bandits that watches and observes and tries to pick the right algorithm in this case. Here's the really fun part. There's a ResNet 50 model that's being used, looking at the raw video scene, to just give this contextual bandit rich context. So it kind of, in some way, sees how many faces by the high-level by the features up to the n-1 layer of the ResNet 50, and then it also looks at the loss function from the utility model as it works. And the contextual bandit runs mostly inference, but it also does an exploit, but also does exploration. So it's actually studying all the time. So as an example of the video here, there's a stream coming into the face tracker. And algorithm 3 here, you see the middle curve here is the actual choice of algorithm. The top is the actual loss function, and the bottom curve is showing the overall entire system latency. And going from a single face right now to multiple faces, and you'll see that these little probes are actually the exploration phase of the algorithm. But what happens is when it gets a bunch of faces here, the algorithm shifts to optimize the utility based on the utility function here. And it gets interesting because it's a pipeline now. It shows a mini pipeline, but you can imagine the future having a big graph. Now, given the bounding box, going to landmark detection, 5 points, 27 points, 87 points, more precise landmarks on a face we need for doing detailed tracking and understanding of the face. The same basic setup now, and what you see here now is an analysis now of looking at 2 modules, and so you can see we now go to 12 different algorithms because it's a combination now. But again, going from many faces to one face, the system is in real time doing all this learning and responding with the contextual bandit based on some theorems and proofs done about what we expect from contextual bandit models. The long-term goal here is to take a big graph someday, built in Psi, let's say, the preferred platform of choice for integrative AI, TM, and automatically have a system adjust how long each module works, what sub-algorithms are being selected to overall optimize the performance of a whole system. Just briefly, I'll end by saying that I've been fascinated by this idea of ideal models of computational anxiety, what an agent should be worrying about when it has a little bit of idle time, even when it doesn't have idle time. So the example I often give is a trauma care surgeon is working on a patient, and a speaker lights up, and there's a multiple casualty case coming in, ambulances and a family coming in. And the trauma care surgeon might stop or slow down this case to just start directing resources for that next case coming in as the ambulance is on its way in, or multiple ambulances. So you even want to reason about when you slow down what you're doing now for the sake of your overall life history of your responses to a stream, for example, in this case. So reasoning about probability distributions over what's happening in the future and speculating is important. And there's some nice theorems and ideas about this that actually would apply to speculation more generally in the systems world, which is so important in systems, often done heuristically, taking algorithms from the AI community and applying them in this way. If you could do what we call continual computation, using every single moment ideally over time, given your current tasks and a probability distribution over future tasks, to me, first of all, that's a real model of intelligence. Because we're not here to solve, most of us, one problem and then die. We're here to survive and have a rich, long history of successes. And we want to always be dreaming about the future, trading off the now for the future, and being ready for the probability distribution of what's coming next. And there's some nice, even some basic assumptions about distributions and about our value of pre-computing them. We can do quite a bit with optimizing our life histories. And so these ideas have been applied to prefetching of web pages, to pre-computing sets of questions that you might ask in a like a medical diagnostic system. It's really hard to compute, for example, the value of information. Applying this to navigating through a geo database, for example, very quickly, where you get a sense by a trajectory where someone's going, and you get a sense for a probability distribution of needs and potential page hits and misses, or even a gaming engine in the cloud where you know the rules of the game, you know the graphics, you know the needs, and you can actually start to use these principles to fetch ahead. One application that we're very excited about, I went from old research to last week publication at PNAS. We just published this work, and this work came from some work from 1998 in SICM, 2007 at AAAI, and now PNAS, building on the same set of ideas. But the idea is very core, and I'll end with this concept here, very core notion in systems. How do we keep a cache fresh? Think about this. Or the same challenge is, how do we keep our index of the web fresh? How do we run a web crawl? It's a very interesting problem of an agent in the open world, or multiple agents. And the idea is you have, let's look at the web problem, many pages with some knowledge about page change rates based on their properties and history potentially. And you also have knowledge about how popular a page is. What's the utility function? It's a function of how old a page is, of the cost, and how often it's being to be looked at. Turns out that to solve that problem, it's generally a very hard optimization problem. Cho and Garcia Molina showed for small n how to optimize that problem. And Azar here with Yuval, myself, with Dr. Shahaf, with some interesting new results, have showed an n log n version of this that's running at 99% optimal. It's a randomized probabilistic strategy. It's amazing. This is for synthetic data, but we're now, I should say, Andre's trying this out with real data. Andrei Kobolov right now working with us. But this upper curve here is opt, and it's n log n methodology as well, showing how well we can do with a probabilistic continual computation policy. Very exciting. So there are rich opportunities in applying AI for AI systems, and I was going to say AI for systems as well. Getting down to the bare metal, which is refreshing a cache. Thanks very much. Oh, do you think questions now?
Yeah,
or?
We have time for a couple of questions.
Sure. So there should have been, in that potpourri, something for everybody. Yeah. Oh, hi.
If nobody asks, I will ask. You and I have been in this business for a long time. So you ended your talk on a very optimistic, futuristic fashion. I am more concerned about who knows how long I will be around, and so I'm more concerned about next 10 years, let's say. And I am a little concerned that in that respect, we are a little exuberant and over-optimistic, because what you as a company and I as a customer want is some kind of guarantees that what you are going to give me will work not 99%, but 10 to minus 3%. And I am a little disturbed, especially coming from academia, that we sometimes oversell. I am disturbed when I hear that we can recognize with 85%. When I was young and we did simple pattern recognition, that was not considered a result. And you must remember that. So I'm a little concerned that we don't show that under what conditions we can guarantee that this will work. And you started your lecture with robustness, okay? And then you kind of abandoned that word at the very end. But I really think that in order for us to get credibility in the population at large, we really need to go back to the guarantees and robustness. Sorry, I hope I didn't.
Well, we should have a long discussion about this, but let me start by saying I only abandoned robustness because that was only the first topic of 4 in 25 minutes. It's a very important topic for the community, and there's two approaches to it, several approaches, I should say. Let me point out the work by Besamir Anushi right now, who just gave a paper at HComp, which is building on a nice, rich history of work, which is really, really dissecting down, introducing new levels of accountability to machine learning for well-calibrated and reliable error signals based on context. So it's a very important area for us. It hasn't been announced yet, but we'll be kicking off a significant effort with MIT CSAIL called Trustworthy and Robust AI. So we're not abandoning that topic by any means, just because it was the first topic on my slide deck.
Come to us. That's what we do.
We are very close with our Berkeley friends as well. And there's more discussion to be had about that, by the way, but offline. The other comment is, if you have a well-calibrated error signal, it probably doesn't make a difference how poor your inference is. That just changes the application and the design and the appropriateness of using a technique. The hard problem is being aware and sensitive and having subsystems and supersystems that understand how to compute the reliability signal. And this is a very powerful and important area for our research here, and we can talk more about that also offline. Thirdly, I'll say, and we can go on again for a while now, Microsoft has been a leader externally, co-founding the Partnership on AI, where just today I tweeted, if you want to look for my tweet, the working group on safety and reliability published its document, its charter to publicly. That group happens to be a multi-party stakeholder group involving civil society as well as technologists. But this is a very important topic. I'll say that at Microsoft we have what's called the Ether Committee, AI Ethics and Effects in Engineering and Research. And safety and reliable systems is one of 7 working groups, very active, co-chaired by Ajay Kumar, who's been working in this space for a while also. So you're asking the right people to be concerned. I think it's a good concern, and we're with you on it. So, and we'll talk about Berkeley later, offline.
I just want to say that when my PhD students, when they present their results, the standard question I have, don't show me what you can do, show me what your system cannot do.
Right. And as a warning to the whole AI community, people that do duplex demos or whatever demos you want to do, and to people who call out the problems with AI, it's easy with probabilistic systems to do a complete video and expose of how terrible a system is by picking some examples, and how wondrous it is if you just pick the good examples. And so we want to always be cautious about that and give people a good representative understanding of how well things do. And that's part of even coming up with a reliability score, I think. So great question, and we can have a longer discussion maybe later about that, but I'm getting the sense that I'm actually giving Virginia even more time than she needs usually for AV problems. Okay.
So thank you very much, Eric. So next we have Virginia Smith, and she is going to be faculty. I mean, she already actually started as faculty at Carnegie Mellon University, and she just finished her thesis with Mike Jordan in Berkeley, and we are very excited to have her here. And thank you for flying out from Pittsburgh. I know it's hard because I used to go to grad school there. And yeah, I'll let you.
Thanks. Can everyone hear me okay? Great. Yeah, so I'm excited to be here. Thanks for the introduction. Today I'll be sharing some of my work in developing system-aware optimization methods for the federated setting. So the motivation for this work and for a lot of my work is thinking about the machine learning workflow and trying to make it more efficient and more robust and more reliable. So what do I mean by the machine learning workflow? This is a very coarse description of the workflow. You start with your data set and a problem that you'd like to solve. Let's pretend it's something with cat pictures. That tends to happen a lot. Under the hood, then you select your machine learning model. And then to actually fit that model to your data, you often have to select an optimization algorithm to actually train that model. Okay? But often this workflow is not happening in isolation. It's happening together with some sort of system. And this system and the parameters of this system have a very large impact on the optimization algorithm that you select to fit your model to your data. So one area that system-aware optimization has a great potential to really improve things is the federated setting. So in federated learning, this is just a term that's been coined to describe the problem of training machine learning models at the edge. So as opposed to a traditional cloud-based training where you might be storing a model on the cloud and training on the cloud, when it comes time for prediction, you send raw data from the devices, and then you get the predictions from the cloud. Here we're trying to push some of the computation and offload it onto the devices themselves. So you can store the models on the devices, and you can also perform training at the edge. So what that looks like is instead of actually shipping the raw data, you can send sort of downstream model updates and aggregate them via the cloud, and then come to consensus on some sort of global model that you ship back to the devices. So this is becoming more and more feasible as devices grow in terms of their computational capabilities. It's a nice thing to do because it allows you to quickly incorporate new data that you're seeing on the devices. It also helps to reduce the strain on the network because you're not having to ship this raw data. And it helps to increase the privacy guarantees that you can provide. Again, because you're not shipping the raw data, you're shipping these downstream model updates. So what are some examples of applications that fit into this sort of setting? You can imagine things like language modeling for speech recognition on mobile phones, adapting to pedestrian behavior in a fleet of autonomous vehicles, or predicting health events like low blood sugar from wearable devices. So not all applications from the IoT setting fit into this setting, but many do. And the key sort of assumptions are that the local data that's being generated on each device is important, potentially more so than some proxy data that you could use if you were training this model just in the cloud. For the problems that we're looking at supervised problems where labels need to be available. And then another reason why these types of problems are becoming more and more interesting is that privacy is often a very important concern. And so not having to ship that raw data for applications like this helps to enable privacy guarantees. Okay, so what makes this problem difficult? Why is it difficult to solve optimization problems in the federated setting? In particular, why is it that we can't use traditional distributed optimization methods that have been developed over the past decade and more that have been developed for the data center setting? The issue is that traditional data center distributed optimization methods face a suite of new challenges when looking at the federated setting. So in particular, in the federated setting, communication can be more expensive than in the data center setting. So you might have, rather than hundreds to thousands of machines, you might have thousands to millions of devices in the network. And the network itself can be slower than a traditional data center. So you can imagine a mobile phone network where some of the phones have very poor network connection. Additionally, there's a huge amount of variability in the network itself. So you might have as compared to a data center setting where you might assume that most of the machines have similar computational power. Here you could have some devices that have very different computational abilities than others. You might have certain devices that are very old versus very new devices, some that have very low battery power or poor network connection. And these things can really affect stragglers in the system, and it can also affect issues like fault tolerance. So at any given round in a network with 1 million devices, you could imagine that many of them, if you're trying to do some sort of computation, are offline or trying to do some other sort of computation. So you can't count on them for computation at every round. So fault tolerance is a big issue in this setting. And I'll note that this heterogeneity, this variability, comes not only from the system's perspective, but also from the statistical point of view. The issue here is that we're generating data on these devices, and we're also trying to store and process that data. And so some devices might generate much more data than the others, and this can lead to very unbalanced data across the network. So the statistical unbalance presents issues in terms of how we actually solve this optimization problem, but it also presents issues in terms of how we model the problem. So in particular, personalization is really key in this setting. The data that's being generated on each of these devices can be generated in a very non-identically distributed manner. So you might have certain devices that generate data that's very different from the others. For example, if we're thinking about trying to develop voice recognition models, my voice recognition model might be very different than someone else's because we're generating different sorts of data. So in the talk today, I'm going to talk about two methods that we've developed recently to try to handle some of these challenges. One is fedCoco, which is a method for handling some of the system's challenges in the federated setting. And the other is Mocha, which is something that builds on these ideas to also allow for personalization. So first, in terms of developing a distributed optimization method for the federated setting, again, what is the issue with using something like a traditional data center distributed optimization method? Well, this is a question that I asked myself because this is what I spent a lot of my thesis working on. So for example, if you look at some results from the data center setting with state-of-the-art methods, you'll see results like this. So on the x-axis here, I'll be showing the time in seconds, and on the y-axis, the distance to the optimal. So the goal is to get down to the bottom of this plot as quickly as possible. What you see in the data center is that if you compare methods that have been developed and tuned for this data center setting, such as COCO, which was the focus of my thesis work, you can get these massive improvements over other traditional methods like mini-batch stochastic gradient descent or mini-batch coordinate descent. Okay, so for example, for this problem and this cluster, this was a 40x speed up. It meant that the training time went from 2 hours down to just roughly 3 minutes. So this makes a big impact in terms of your overall training expense. So these methods work well in the data center setting. Let's see what happens though when we apply COCO to the federated setting. So what you see is that in terms of the time in seconds here to get to the optimal, COCO is not really doing that well, and in particular, it's not doing much better than these other baseline methods. And the reason for this is that there are these additional constraints and challenges of the federated setting that have not been well modeled by this optimization method. So what we'll show you today is basically how to improve upon this with this method that we're calling fedCoco to get these very large performance improvements. Okay, so I'm going to backtrack a little bit now and talk about how COCO works to show you where it's falling short, which allows us to develop this more tailored method for the federated setting. Okay, so the motivation for COCO comes from the fact that there are two sort of extremes currently in thinking about how to perform optimization in the distributed setting. So the goal, again, is that you have a bunch of data that's distributed on different machines or devices. So imagine each of these dark gray rectangles is a data point, and each of these light gray squares is either a device or a machine. The goal is to process all of this data and to try to find the optimal machine learning model, knowing that you have to communicate back and forth with each of these devices at each round. So how can we perform this communication? On one extreme, you could take something basically that works well on a single machine and try to sort of naively parallelize it into the distributed setting. This would be something like a traditional mini-batch method, mini-batch stochastic gradient descent, for example. This method works by, at each round, selecting a data point or a subset of data points at random and computing something like a gradient from those data points, sending those updates back to the master, applying them to the model, and iterating doing this over and over again until convergence is reached. So these methods are very popular, and they're nice because we have nice convergence guarantees about these methods. But in general, they can be very slow in the distributed setting because you'll be communicating very frequently between the machines and the master. So what else is there? On the other extreme, there are methods known as one-shot communication schemes, where instead of processing one data point or a few, you process all of the data points completely. You completely solve separate models on each of the machines, and then you do something like average them at the end. So this is the other extreme. It says never communicate or only communicate once at the end. It's great because it's really fast, but in general, convergence is not guaranteed. So you don't have the same sort of nice theoretical properties that you do from the mini-batch methods. So in putting this together, the nice thing about COCO, the reason that it is a great method to use in the data center setting is that it helps you to go between these two extremes. So in particular, COCO takes this one system parameter of how much do you do local computation versus communication, and it exposes it to make it as flexible as possible so that you can tune this amount of local computation versus communication. Okay, how is COCO actually doing this? So the method is actually very simple. Basically what it does is that the goal is, again, to find some model across all of the data. How can we do this? We can take this global problem and split it into subproblems, one for each machine. So each machine is trying to find some solution to its own local subproblem. It tries to find some updates to that subproblem, sends those updates back to the master, applies that to the model, and then iterates doing this over and over again. But the thing that makes COCO really flexible is that in performing these updates to the local subproblems, it makes the following assumption. It assumes that each of these subproblems is solved to accuracy theta. So this theta parameter is really flexible because theta is just a number that can go between 0 and 1, where when theta is equal to 0, it means that all of these problems have been exactly solved on each device. Whereas if theta is closer to 1, it means that you are inexactly solving the solution. Perhaps you're just doing 1 or 2 updates locally. So by tuning this parameter, you can tune roughly the amount of local computation versus communication. So this seems like a great setup to use in the federated setting where you have this issue of expensive communication. However, there's one issue with this theta parameter, which is that theta is not truly that flexible and that you have to set it once for the entire method. So this theta parameter is consistent across devices and across iterations. The reason that this is such an issue, again, is because we have issues in the federated setting with statistical heterogeneity. Some of the subproblems might be harder to solve than others, which would affect this theta parameter. You might also have issues with systems heterogeneity, so some of the devices might not be able to compute good solutions to their subproblems because they're not connected to the network, they have low power, low battery level, or just their hardware is worse than the other devices in the network. Okay? And finally, you can also have issues with devices actually just dropping off and going offline. And that's not accounted for in the original COCO method, because in COCO, we don't allow this parameter to exactly equal 1, meaning that you have to send some update. Okay, so what do we do in federated COCO to handle this? Basically, we make this simple change. So we change theta to be something that you can vary both by iteration and by device. And this looks deceptively simple, but what becomes difficult is actually showing that the method can still converge given that you've done this. And what we're able to show is that using this much more flexible accuracy parameter with the simple assumption that the same device doesn't not send information every single round. So you have to eventually get an update from one of the devices. Otherwise, you won't be able to reach the optimal. We can show 2 convergence guarantees. One for L-Lipschitz losses. This is something like the support vector machine model. You get a 1/epsilon rate of convergence. And you can get a slightly faster rate of convergence for smooth losses, things like logistic regression or linear regression. Okay, so this is nice because now we have this setup that is much more flexible and more tailored to the federated setting. And we have nice theoretical convergence guarantees about it. But how does it perform in practice? So what we've done is we've gathered some real federated data sets from things like a sensor network, Google Glass data, human activity recognition on mobile phones. And you can see what's interesting is that these real federated data sets really are quite heterogeneous. So you can see that the minimum and maximum number of data points per device really does change significantly. For these data sets, I'll just show one example of the results. You can see that federated COCO, in terms of the time in seconds, is able to converge much faster than traditional COCO and these sort of very popular mini-batch style methods, which are used frequently in the distributed setting. So in particular, for this problem that we were looking at, we're able to converge to the same epsilon accurate solution 2 orders of magnitude more quickly. And what was interesting is that we also got to look at what would happen if we just dropped devices out of the network. How would that change the performance of the method? And what you can see is that as long as we don't drop out one device every single round, which is what is shown in this green dotted line, the performance of federated COCO is fairly robust to this issue of devices dropping out. Okay, so I wanted to talk briefly as well about what we've done to handle personalization. So going back to this workflow, one thing about the federated setting is that it's really impacting not only how we solve this optimization problem, but also how we model the data itself. Okay? And so thinking about how to model federated data, 2 extremes are, you could imagine just selecting a separate model for each of the devices in the network. This is nice because it allows you to personalize to the local data that you've collected, but it's not great in that you can't really learn from the other devices in the network. If you're learning a separate model for each of the devices, then you're not able to aggregate the information and learn across the devices. On the other extreme, if you learn just a single model for all of the devices, you're helping to learn from the peers in the network, but you're not really personalizing the information that you have. So what we want is something in between. We want to be able to personalize our models, but also learn from the aggregate information and boost the effective sample size of each of the devices. So how are we doing this? One nice way to set this problem up is through something called multitask learning. So in multitask learning, you do exactly this. Basically, you're trying to find some local model for each of the local data sets. These local models are all captured in this aggregate matrix W. And then what the objective is doing is basically enforcing that these models follow some structure, where structure is enforced through this task relationship matrix omega. So the reason that this is really nice is that you're trading off between trying to find the optimal models for each of the devices, as well as enforcing some structure across those models. So this allows you to have personalized models that also share and learn the structure across them. So this setup, for example, can capture things like all of the tasks being related, most of them being related, but there being some outliers, clusters or groups, or things like asymmetric relationships. For example, you might have a power user in the system that is performing most of the interesting information. So you can capture relationships like that as well. Okay, and we looked at using a multitask setup with the real federated data sets that we had collected. And what we saw is that the multitask setup compared to the completely global or completely local models consistently got better prediction error in terms of the problems that we were looking at. So you can see this right-hand column, each of these prediction error numbers are significantly lower than the other 2 models. And this makes sense because the multitask setup is really able to go between these 2 extremes of a completely global or a completely local model. So with this in mind, the key question then was how can we take this nice multitask learning framework and apply it to some of the federated COCO work that we had that is looking at trying to actually solve this problem in the federated setting. So in particular, we want to be able to solve this new, broader objective in the federated setting. If we're looking at this objective, one thing that's nice is that if you solve for these 2 terms, competing terms, W and omega, in an alternating fashion, omega is in fact quite easy to solve. You can solve that just with the models W, but without access to any of the federated data. But W is what needs to be solved in the federated setting. So the key question was, how can we extend this update to W to work with the federated COCO method that we had described from before. Okay, and I missed kind of the key idea of how we actually form these subproblems when I was describing them earlier. And this is really important if we want to think about extending it to another type of objective. And so recall that the way that federated COCO and COCO work is that basically you have some global problem of interest. The way that you actually solve this global problem is by splitting it into subproblems, one for each device. And so the way that this division is happening is actually very closely tied to the mathematical formulation of the objective function. So in particular, what we do in COCO, which is nice, is that the primal problem here is a bit difficult to solve. It's a bit difficult to distribute this into separate subproblems because you have data points that are touching each of the models of interest W. And so what you can do is instead of looking at this primal formulation, you can instead consider the dual. So this is a very common trick that's often used in optimization. Because this problem is convex, the dual will still arrive at the same solution as the primal. But this dual is actually much easier to separate because you have one dual variable per data point. And so this separates much more nicely across the machines. Okay, so what I'm saying is mostly true except for this regularization term here. And the way that we handle that in COCO is by doing a quadratic approximation to this term. So essentially what's happening is that at each iteration, we're computing a quadratic approximation to the true objective in the dual. Okay, so that's kind of the secret sauce in the back of how we're actually taking this problem and distributing it across the devices. But it's important to consider this because then the key challenge is how can we take the same idea of using the primal and the dual and apply that to this multitask learning objective. Okay, and I'll just summarize this quickly by saying basically we can do something very similar where the dual of interest looks like this, and we can define a subproblem very similar to what we had done in COCO and federated COCO, where basically we're looking at this dual and forming a quadratic approximation around it. Okay, so putting these all together, just to kind of recap, this was nice because we addressed some of these key challenges in the federated setting that really differ from the data center setting. In federated COCO, we handled things like expensive communication by taking the problem and putting it into these subproblems that are solved to approximate accuracies. And we allowed these approximate accuracies to be highly variable, which helps to deal with systems heterogeneity. Then with MoCA, we also looked at the statistical issue of personalization. And we showed that we can take that model and also apply this similar ideas as in federated COCO. So I'll end with 2 quick slides in terms of where this is going next. So I'll note that there are a lot of other exciting areas and open research opportunities in federated learning. So one is that the problems I talked about today were all convex. Deep learning is also, of course, very popular and is non-convex. So there are interesting opportunities in thinking about how to extend this to the non-convex setting. There are a lot of interesting open problems to deal with privacy and security around a solution like this. So certainly federated learning improves upon sending just the raw data, but those model updates, you also want to make sure that those are secure. We talked about personalization through multitask learning. There are other ways to provide this, like transfer learning or model fine-tuning. We reduced communication by making this accuracy parameter very flexible. There are other ways to reduce this even further, things like compression or lazy aggregation. And finally, in terms of the machine learning pipeline, I've been focusing on the training portion. There are, of course, other ways you could think about addressing the machine learning pipeline in this edge scenario, things like doing on-device feature extraction or on-device inference. So there's a lot of open and exciting research directions within this area. Okay. In terms of my own research, I'll note that one thing I'm excited about is you may have noticed some of the federated data sets that we were looking at were very small. And so we've been working with some collaborators to develop something called LEAF, which is a benchmark for federated data. It will contain a suite of open source data sets, an evaluation framework to help frame some of the statistical and systems metrics and questions. And it will be online very soon. So please check back on my website because we'll be releasing it in the next few months. And sorry, last thing. So There's been a lot of exciting work around systems and machine learning, obviously at the summit today and within this session. I myself am serving as program chair for a new conference on systems and machine learning called SysML. So SysML, the goal of the conference is to elicit new connections between the two fields and to make sure that these discussions are happening not siloed within their own research communities, but in a collaborative way. So this last year, we held a one-day conference with over 300 attendees and 200 submissions. This next year, 2019, will be a full conference, 3 days with published proceedings. So if you're interested in that, please take a look. The submissions are due at the end of September, and the conference itself will be in Stanford in the end of March through April of 2019. So thanks, that was all I had, and I'd be happy to answer questions. Yeah.
So I had a question about the privacy aspect of the federated approach. I mean, it seems to me that if I'm worried about the privacy of my data, then it should only be used locally, right? And especially if it's going to be for a personalized model, right? And not be shared at all with the cloud. But sending model updates, it seems to kind of like open a whole can of worms with like model inference attacks and things like this, where it's not really clear you're not going to be leaking basically that data.
Yeah, that's a great point. I think there's a trade-off there. If privacy is the most important thing to you, more important perhaps than the accuracy that you're getting, then certainly it makes sense to keep that data completely local. The main thing that the federated setup is positing is basically that sending model updates is a better alternative than sending the raw data, which is what's frequently done in a cloud-based situation where you have the model in the cloud and you're sending the raw data up to get predictions. So I agree with you that the model updates themselves could also be an issue. And so there's some interesting work looking at combining that with differential privacy to ensure that the model updates that you send are in fact private. But I think that there's a trade-off because if you keep all of the data completely local, then you're losing some of the interesting information and data that you could get from devices like yours. So, yeah.
I have a question about the personalization. So I'm not a machine learning person, but can you give some examples? So I'm kind of trying to understand what the limitations of it is in terms of, is this about different phones having different types of sensors or people having different preferences? So
yeah, so I think the example I gave before was that, for example, if you're trying to train a model for voice recognition on your phone, if you train a single model for voice recognition across all voices, it could be that that doesn't perform as well as one that's personalized to the specific voice of a specific person. And so certainly there are some aspects of speech that are going to be the same across all people, but you could also imagine that certain aspects of the way that a person speaks or their accent also influence speech recognition. And so that's the trade-off where you want to do some global modeling, but also have some amount of it that is local or personal to the data. Yeah. Thanks.
Thank you very much. And then we're going to have our next speaker. I'm very excited to introduce Behnaz Arzani, and she's from MSR as well, and she's going to tell us about self-managing networks, and hopefully we'll not have any networking problems ever again. Except we have AV problems.
But this doesn't work, seems like.
Oh, you have to. Oh,
I did.
maybe you have to do.
Yep. I have one in my bag. I can use mine, but let's see. I'll put it on. I can use my own too, but
Yeah.
let me go. Actually, this is recognizing, but let me grab mine. Sorry. Is my bag somewhere around here? Sorry. No, my bag isn't there. Okay. Never mind. It used to be there. Okay, I can just use my hands. That's fine. Okay. Sorry, everyone. So today I'm going to be talking about, this is more of a networking talk. I'm not really a machine learning person, but what I want to talk about is how we move towards networks that can manage themselves. And what I want to do is sort of talk about what I've learned through my research about where machine learning can actually help in networking. So the picture I have here is of Albert Greenberg, and he's the head of Azure Networking. And he has 1,029 reports. And if you look at what these people do on a day-to-day basis, a lot of their time is spent on managing and configuring networks. And if you think about when networking as a field started, the first paper on networking was in 1973. SIGCOMM started in 1969. Sigmetrics has been around since 1971. And then NSCI started in 2004. And yet, we still need people to actually actively configure and manage our networks. So what I wanted to do is to try to understand, why do we still need this? Like, why are people spending so many hours and so much money just on configuration and management? And so what I'll do is I'll talk about what my research in collaboration with Azure over the last 3 years. And what I'll describe is what I've learned to be the cause of this problem and where machine learning can come into play to help solve it. And this has a couple of different aspects to it. One aspect is diagnosis. The other aspect is security. And then I'll talk about what were the common themes and how can actually AI help with it. So I borrowed this slide from Amin Baghdad, who is basically the counterpart of Albert in Google. And according to him, availability is the main foundation on which our data centers are built. So we want them to be manageable, we want them to be performant, but if they're not available, we get none of that benefit anyway. And so the first thing that can disrupt that is going to be failures, right? So failures are going to hurt our availability. And to give an example of why it is that diagnosis is hard is, think of this scenario. You're a researcher, you want to use the cloud. You boot up a cloud VM, you go over the cloud network, and then you connect to some service. And so when something goes down, if you imagine that the network is managed by Azure, and then the service could be managed by some other company, the problem that this causes is when you have a failure, you can have one of two situations. Either someone accepts responsibility for the failure. So either the network operator looks at their networks and figures out, oh, I know why this happens. Or on the other hand, the service operator looks at their system and finds a cause of the problem. And in that situation, you can eventually figure out what was the root cause and solve it. But often, you run into this particular situation where the network starts blaming the service blames the network, and nobody really wants to take responsibility for this. And we had a real example of this happening in Azure Networking, where we had VMs that were connecting to virtual storage panic and reboot because their connections to storage were failing. And in these situations, we had tickets created that were basically showing customers are being impacted, but nobody was willing to take responsibility for it. So storage was blaming network was blaming storage, and the problem was not getting resolved. So the question was, how can we actually attribute blame to the right team? So we created a system that was published in SIGCOMM 2016. We call it NetPoro. And the main requirement for it was that it didn't require anything to be installed in the network or storage, because neither one of them wanted to have that overhead, but would still be able to say who is responsible for the failure when the failure happened. And what we decided to do is take advantage of a network protocol called TCP. Now, TCP is designed to be able to detect network failures. It's designed to be able to give you reliability when you're going over a best effort distributed system that is not guaranteed to deliver all of your packets. But then our theory was, if it's designed to detect failures in the network, can it distinguish between failures in the network and failures on the server side? And so we took a bet. And what we did was we designed the system that looked at TCP statistics we gathered from the host, so it doesn't gather any data from the network or the service, and try to identify if we have a client-side failure or a server-side failure or a network failure. So the way the system worked is we had a monitoring agent that was deployed on all hosts across Azure, all Azure data centers. And we injected failures onto a subset of these machines to look at what failures look like in terms of TCP statistics. And then we trained a simple random forest model using this data to see if we could actually distinguish what was causing the problem. And then this model was running on each of the hosts to figure out why the VM is rebooting. And it turned out that to work really, really well. So while we solved that problem, we still had one more, which was, OK, now I know that I have failures in my network. And it turned out actually 20% of the time those failures were in the network. Then we ran into a separate situation where you could have multiple links in your network having failed or be dropping packets at any given point in time. And you can actually have a link with a high drop rate and a link with a slightly lower drop rate. But you care about one of them more, because while the link with high drop rate is dropping a lot of packets, it's not impacting any customers, or the customer is not noticing that packet drop rate. Versus this other lower drop rate packet is impacting a customer whose application is very, very sensitive to this type of failure. So what we wanted to be able to do is associate failed links with the problems that they're causing. So essentially, we wanted to say this customer is impacted by that link failure. This customer is impacted by this link failure. Now here, we actually didn't use machine learning, but I'll talk about how we actually solved the problem. But before I do that, I'll talk about why it's actually hard. So in an ideal situation, what you want to do is say, this is the connections that this guy has. These are the connections that this guy has. If I know where my failures are, I can basically map the failure to the connection and then solve the problem. But the problem is the operators don't always know where the failed links are either, right? And if you think about the scale at which data centers operate, this becomes an extremely hard problem. It's basically like finding a needle in a haystack. And the thing is, we also have packet drop rates that are because of the normal day-to-day operations of the network. So tail drop rates happen, and detecting them doesn't really give you anything. You can't take any action on those types of problems. So one-off transient drops do occur on many links, and they add noise to the diagnosis problem. And so the requirements that we were asked when we were solving this problem was to be able to detect short-lived failures, to be able to detect concurrent failures, and we wanted the approach to be robust to noise. But again, like the previous approach, we again had this mandate from the network operators where we were not allowed to deploy anything on the servers or anything on the network. So we had to again use an approach that was only on the client side. So the strawman solution to this would have been something that is traditionally in networking known as tomography. The way it works in this example is the following. If you have a simple topology where the link between 4 and 2 is bad, and you have 3 connections, you can basically assign a variable. Let's assume you know the path of each of these individual connections for now, right? You can assign a variable to each of the links, and you can form a system of equations that equate 0 if there is no failed link along the path, and equate 1 if you have a failed link along your path. And by solving this system of equations, you can basically figure out which links in your network have failed. So the easiest reason why this fails is that you don't always have enough flows to be able to have a solvable set of equations. There are more problems beyond this from a networking standpoint, in the sense that it's really hard to have the path of every single flow in your network and a lot of other things. And I won't go into the detail of that to bore you. But we had a system we call 007 that was published in NSCI 2018 that basically tries to solve this problem. And I'll just give you a teaser of how it works. And the way it works is we have, again, an agent that's only on all hosts in Azure, so it's on the client side. And it monitors TCP connections running on these hosts. Every time there's a packet drop, this agent gets notified that a packet drop happened. And the hosts then vote on the status of the links. So the way the voting works is, in this case, this connection didn't experience any failures. All links get a vote of 0, 1, and 2. And we actually have a theoretical guarantee that this is supposed to work, that it's resilient to noise, all of the stuff that operators care about. Now, in the context of security, I've also been looking now at a problem, again, in collaboration with Azure Networking. And here, this is a completely different flavor than what I was talking about earlier. What we want to be able to do is to detect compromised VMs. It's a very simple problem. And if I have anti-malware on all of my VMs in an ideal situation, I really don't have a problem. Anytime my VM gets compromised, the anti-malware should be able to find it, and I'm good. The problem is that in reality, this is what the system looks like. A lot of customers don't want to have a Microsoft-owned anti-malware software on their machines. So a lot of these VMs are not protected. So then the question is, how do I protect those VMs? Because these VMs can now cause damage to other VMs that are running in the same data center. And the way we decided to do this was based on a theory. We thought that if compromised VMs leave a network footprint, then maybe the connection graph changes significantly enough when a VM is compromised from its past behavior for us to be able to detect it. So this is ongoing work, but right now the results seem rather promising, so we don't know if it will work or not. But what I want to do, now that I've talked about the general scope of the problems I've worked on, is, one more slide. What was the common themes across these problems and where machine learning can actually help? So before I go into that, I found this RFC. For those of you who work on networking, you know that RFCs are basically standards in networking. And they're basically, it's from 1996. So it's even before, I think I was 5 at that point, maybe. But I feel like the truths that are said in that RFC still hold. So first of all, some things in life can never be appreciated or nor understood until you actually do it yourself. One of the things that I've learned after 3 years of collaborating with Azure Networking has been until you experience the problems, and if you don't have the domain knowledge, it's going to be really, really hard to create a solution that the operators actually want to use and is practical. The second thing is, it's always possible to have multiple separate solutions to the problem and try to combine them. But when you work with operators, one of the things that you would notice is that they always prefer the simplest solution. You can provide complex models that work really, really well in theory, but in practice, an operator should be able to verify why your model is not working. So if I'm an operator and if I look at a number coming out of a system and I don't know what it means, if the system gives me a wrong number at one point in time, I'm going to lose confidence in the system and I'm never going to use it again. And that happens a lot. So, but going back to the original question I asked, which was, why do we need operators to manage our networks today? There are a couple of reasons. First of all, the ideal data that we need to figure out the cause of problems is often missing. The monitoring we need is expensive a lot of times. And so one place that machine learning can really, really help is figuring out when and where to initiate monitoring of what type of data. The other thing is gathering the right data can be expensive. So that's another place where I think we can contribute. Sometimes it's not even clear what the right data is to figure out the source of a subset of these problems. And there's sometimes, like the case in NetPoro, which we found, is that there's data that indirectly points to the cause of the problem. And sure, causality is important, but sometimes correlation is just enough, and it's all that you need. So to sum it up, this is where I think AI can help. If you can predict when a failure is about to happen, we can always figure out what monitoring to turn on and what that monitoring should be. If you can identify where the complex correlations are, and if you can, sometimes it's the case that you can't avoid operator involvement. Sometimes the operator is needed to solve a problem, but if you can identify when that help is actually needed and when the alert is noise, that would reduce pain in complex platforms like Azure by a lot. So with that, I'll end with this other truth that I find is important to keep in mind. Thanks.
So there's a lot of new work coming out in like model interpretability. It's a very hot topic in the machine learning area right now, like interpreting the output of models, including deep learning or even other. Whether deep learning or otherwise, like how do we interpret, especially like complex decision trees and everything, right? So do you see that, like do you find like that kind of work still being useful, or is it still too far away from like really helping this domain?
So the way that there's two ways I find this useful, and one of them is slightly idiotic. And the one that I find it most useful is when you want to build operator trust in your system or in your model, it helps if they understand why it and how the model is working, or when it's not working, why it's not working, right? And that is a place that I think that's very much needed. I've seen a lot of systems built by Azure Networking themselves where the system is deployed, it's very useful, it makes a couple of mistakes, and people are like, oh, this system is crap, we're never going to use it again. And that's not really true, but it's like people lost confidence in the system, so they're never going to use it again, right? So that's one thing. But the other thing I think is sometimes, like in the case of the TCP stuff, the NetPoro stuff that we did, you can gain a lot of knowledge about the protocol itself or about the fundamentals of the system itself from the explainability of the models. Like what we learned was a lot about how TCP reacts to failures on the server side that we didn't know before or didn't expect to see. So that was also something like, and that's part of the reason we use decision trees, because they give you explainability. But yeah, so those are the things I think where this can be used.